In this section, we're going to take a closer look at rational functions and their graphs. Remember that a rational function is essentially just a polynomial divided by a polynomial. So a fraction with both numerator and denominator being polynomials. Here's the definition again. If p of x and q of x are polynomials, and q of x can't be the zero polynomial, then the function f of x, which is p of x over q of x, is a rational function. And what is the domain of f of x? The domain of f of x, I'll write this in set builder notation. It's the set of all x values that are on the real line, all the real numbers x, such that q of x is not 0. Of course, q of x can't be 0, because then we would have, for certain values of x, we would have a 0 in the denominator. But every other number is good. Every other number is part of the domain. So the domain is all the real numbers except for those x values, giving a q of x equal to 0. Okay, let's do just some review here of rational functions. Let's find the domains of these three rational functions. This one should be very simple. Remember, you don't even have to look at the numerator. You only have to look at the denominator. This x squared minus 5 is like p of x. It's q of x we're concerned with, x minus 5. And if you set x minus 5 equal to 0 and solve, you're going to get x equal 5. And what does that tell you? 5 is not in the domain, but every other number is. So the domain is all real numbers except for the one number 5. Another way of writing that would be, or you could say negative infinity up to 5 unioned with 5 to infinity. This is the entire real line. The only number not included in one of these intervals is 5. Remember, this parentheses means this is an open interval. 5 is not included in this set, nor is it included in this set. So you can write it either way, the domain. Let's now look at the domain of G. The domain of G. Okay, the first little scratch work I have to do is figure out when is this thing equal to 0, the denominator. When that is the case, that's my bad numbers. Those are the numbers not in the domain. It'll be all real numbers except for the numbers that give me a 0 in the denominator. So x squared minus 5 equals 0 means x squared is equal to 5. And if we use the square root property, we get x equals plus or minus radical 5. Those are the only two bad numbers. If you square radical 5 or negative radical 5, you get a 5. 5 minus 5 gives you 0. So what's the domain? All real numbers except for negative radical 5 or positive radical 5. I could have just said plus or minus radical 5. That would have been perfectly fine in here. It's all real numbers except for these two values. And if I were going to use the interval notation, it would be all of the numbers. It would be an interval from negative infinity up to negative 5 with parentheses, union negative radical 5 to radical 5, union radical 5 to infinity. So it would be the union of three intervals. All right, how about this case? We look at the denominator. This is the function h. We set that equal to 0. And what do we obtain from this? When is this equal to 0? Subtracting 5, when is x squared equal to a negative number? Never in real numbers. Is that true? So, domain, all real numbers. You can't get a 0 down here. Because when you square it, the real number, it gives you 0 or a positive number, plus another 5. You're always going to have a positive number here in the denominator. Okay, It's very important that you remember how to get the domain of any rational function. All right, let's look at an example here. Let's graph the function f of x equals 1 over x. And this is a rational function. The numerator is the polynomial 1. That'd be considered a 0-degree polynomial. And the denominator is x, which is a first-degree polynomial. So you've probably seen the graph of this before, but let's go over it. First, what is the domain of f? Can you plug in all real numbers into this function? No, it's got a fraction, and it's possible that the denominator could be 0, and that would be a bad number, not in the domain. So the domain of f is all real numbers except for the number 0. All right, so if we were to plug some numbers in, but let's make this easy. This has a name, this function. It's called the reciprocal function. If you plug in number 5, what comes out? 1 over 5. It's reciprocal. If you were to plug in 1/2, you would get 1 over 1/2, which is 2, the reciprocal of 1/2. The f of -3/4 would be -4/3. So it's very simple. We really don't need to make a table of values, but maybe we should. X and y. F of x is just y. So let's do the obvious easy one. When x is a 1, y is a 1. Now let's say when x is a 2, it's 1/2, y would be 1/2. Let's jump out to 10, would be 1 over 10. And now we can't plug in a 0, but let's plug in a fraction. Let's plug in something like 1 over 4. The reciprocal of 1 over 4 is 4. That's probably enough positive numbers. Let's go ahead and start. These are all ordered pairs. 1, 1, that point right there. 2 has a height of only 1/2. 10, the function value, 2, 3, 4, 5, 6, 7, 8, 9, 10, is practically on the x-axis. It's 1/10. I could actually plug in more points. At 3, it would be 1/3, slightly lower, slightly lower, slightly lower, and so on. And if we do fractions between 0 and 1, we're going to get big numbers. For example, 1/2, which I didn't do in this table, the reciprocal of 1/2 is 2. The reciprocal of 1/4 is 4. And you can see that as you get closer to 0, the function values get bigger and bigger and bigger. So if I did 1/10, it would be something like almost right there on the y-axis. This one's kind of hard to graph with this small graph paper. So it looks something like that. Hopefully that's visible. Let me darken it a bit. Okay, and there should be arrows at the end of this graph. It goes up and up and up and up and up, and it goes to the right forever. And it'll never quite touch this x-axis. And as it goes up here, as x goes to 0, this goes higher and higher and higher, and it'll never touch the y-axis. All right, so let me make another table of values for negative numbers. Well, if I plug in a -1, I'm going to get a -1. The reciprocal of -1 is -1. If I plug in a -2, I'll get -1/2. Plug in a -10, I get -1/10. Plug in a -1/4, get a -4. So, -1, -1 is this point right here. -2, -1/2 would be there. And I could also have said -3 is a third, -4 is 1/4, -10 is 1/10, which would be right about there, -1/10. And then -1/2 would be -2, -1/4 is -4, and so on. And this graph is going to look like, oops, not very smooth, my graph. Okay, so that is what the graph of f of x equals 1 over x looks like. And I'm going to ask this function at the very bottom here, but let's go ahead and ask it now. Is this reciprocal function, which is f of x equal 1 over x, is it even, odd, or neither? We're going back in time here, a little bit of a review. Well, it's an odd function. And why is that? Because f of x equals 1 over x can be written as x to the negative 1. F of x is x to the negative 1. Every exponent there's only one term here, and the exponent is an odd number. So it is an odd function, which means that if we were to fold over the y-axis, fold this over from here over, and then fold it down over the x-axis one more time, this would exactly meet this. Okay, so now let's ask a couple of questions, and this is really some new terminology. Summary for the graph of f of x equals 1 over x. Okay, well, what does the graph do? This arrow means as x approaches infinity, as x goes to the right, from 0 it goes to the right, think of it going forever and ever and ever and ever. What happens to the height of the function? What is the height of the function approaching as x goes to infinity? Well, here's the height of the function here. Notice that the height of the function is getting closer and closer and closer to the x-axis, which is a height of 0. So f of x is approaching 0 as x goes to infinity. Let's jump down to the third one. What does the height of the function do? What does f of x, the value of the function, do as x goes to negative infinity? As x is going this way, what is the height of the function approaching? 0 again. This time it's approaching it from the negative side. This time over here it was approaching it from the positive side, but it's still approaching 0. Okay, so f of x is approaching 0 as x approaches negative infinity. All right, number 2. What this means on the right-hand side is, notice that x, if you're on the x-axis, you could approach 0 from 2 different sides. From the positive side means you're approaching 0 from this side. The number 4 has you approaching x from the negative side, so it would be approaching this direction. So what is the value of the function, the height of the function as x approaches 0 from the right-hand side? Well, here the height of the function is, it's just barely over 0. It's getting a little bigger, a little bigger. Now it's up to 1, and then it's up to 2, and it goes all the way up to 10. And if we get closer, it could go up to 100 and 1,000 and 1,000,000 and 1,000,000,000. The height of that is going upward with no bound. So that means that the value of the function f of x is approaching infinity as x goes to 0 from the right-hand side. Now the answer is going to be different when you're approaching 0 from the left-hand side. Notice that the height of the function is negative, negative, negative a half, negative 1, negative 2, negative 4, negative 10, negative 100, negative 1,000, negative 1,000,000. Negative, it approaches negative infinity as x approaches 0 from the left-hand side. So it depends which direction you're approaching 0 from as to whether the function is increasing without bound toward infinity or decreasing without bound toward negative infinity. And we already answered this question. Is the reciprocal function an even function, odd function, or neither? It happens to be an odd function.